Well, good afternoon, industry colleagues. Welcome to the SAPVIA seminar on storage PV, on solar PV and storage equals the energy future. We just have the participants joining at the moment, so we'll start in a couple of minutes' time. Again, a warm welcome to everyone who's just joined. I see we're currently at 75 participants and climbing, so we'll just still take a couple more minutes to let people join the session. Great, it looks like we've settled at around 90 participants. So a very warm welcome to everyone from the industry to this storage PV, so solar PV plus storage session, looking at how PV plus storage can be the energy future. And firstly, I'd like to just thank those who have sponsored the event, which is Genesis Eco Energy and RMB. And also to our partners in these events, which is the Energy Intensive Users Group and the Minerals Council. Thanks to all of them for being part of and being and helping to enable what I think has been a very successful webinar series on driving distributed generation. We're quite privileged to have a great range of speakers this evening, well, afternoon. Feels like the evening, it's been a long day. But this afternoon, we're going to have Warwick Pierce speaking to us on rooftop PV potential in the Garden District, Johan Volmerans talking about defection from the grid, Garth Kluter talking about solar PV with storage solutions, Dr. Svet Balekov speaking about battery health monitoring and analytics, Liz Kutsia talking about whether arbitrage is a viable business case, and after our 5 sessions, five sessions, we'll have a Q&A session that I will moderate. For those of you who don't know me, I am Frank Spencer. I'm an engineer and business developer who's been in the solar PV space for something like 20 years already, although really last 12 or 13 years full-time, and have been involved with SAPVIA since her inception about 10, 11 years ago, currently on the board of SAPVIA. Although my full-time job is working for Bushveld Energy, where we are developing local vanadium redox flow battery technology. And before we kick off with our first speaker, I just wanted to show a couple of slides speaking to the size of the South African market. And I think what is quite phenomenal is that an IHS market report published a few months ago shows that South Africa is currently sitting as already the 6th largest market for residential storage deployments. And when you consider who the other 5 are as other massive economies in the world, the fact that South Africa has come in 6th is quite remarkable and points already to the demand, particularly from the residential sector, for solutions to our current energy crisis in the country. And it's the expectation is that this market will continue to grow, but not only in the residential sector, but also in the utility and the commercial industrial space. And certainly, Kim, if you can jump to the next slide, what we're seeing already in South Africa in terms of utility storage is that there could be as much as 1.3 gigawatts, which could be well over 4 to 8 gigawatt hours worth of batteries procured in various utility programs that may close out next year. So this is certainly very, very exciting, I think, for the market, and certainly speaks to the fact that storage is going to be part of our energy future. And hopefully our speakers will unpack a little bit more about how solar will fit into that as well. So having done that introduction, let me introduce Warwick Pierce, who will be our first speaker. He is a principal systems engineer at the CSIR. He qualified as both a mechanical engineer and an economist, and actually holds 3 master's degrees, which is quite impressive. One of them being a master's degree in energy economics and policy from the University of Surrey in the UK. He specializes in techno-economic modeling and transdisciplinary analysis, and you probably need a whole additional paragraph to unpack what that means. But I think really what he's interested in is helping decision makers to make smarter decisions by providing the necessary information to make those decisions through a robust analysis. He has a solid and well-rounded understanding of the South African energy sector, including the emergence of disruptive technologies and procurement. And I guess solar and storage are definitely those. He's been published in a number of peer-reviewed journals, both international and local, and is thus active in driving sustainable development in the energy sector. Thanks, Warwick. Over to you.
Sure. Thank you, Frank. It's quite a lengthy introduction, but it sounds impressive when someone else says it, but thank you for the introduction. So the first thing on top of this is just to say that I've been off-grid for 3 years now. So you'll notice that we're talking about rooftop PV potential. We're not actually including storage, but just from a personal point of view, I've been off-grid for 3 years, so I can speak from that point of view. But what we're going to be focusing on today, and it's going to be quite data intensive, so I apologize in advance if there's too many numbers. But essentially what we wanted to do is we wanted to ask a few questions and get a few answers. So the title is Rooftop PV Potential in the Garden Route District Municipality. So to give some context to that, where's the Garden Route? Most of the people know more or less what the Garden Route if you're living in South Africa, and off of Pretoria goes to Mossel Bay for sort of the December holidays. So you'll see it's at the bottom there, but it's sort of the Western Cape. And it consists of 7 different municipalities: Kananaland, Tessiquai, Oudtshoorn, Mossel Bay, George, Nyasa, and Bito. Bito is commonly known as Plettenberg Bay. So just to note that this project was funded by GIZ with co-funding coming from the CSIR, which also receives funding through DMRE, so quite a few stakeholders. So what we tried to achieve, and this is the bigger study that was done, and we'll focus on one part of the study, namely Rooftop PV Analysis, is what we're calling a municipal electricity master plan. So you can see it like a mini IRP. We did the same thing, but just for this region. So we see this region in isolation and say, what is the best for this region? So first thing to note is that this provides possible electricity futures, not one truth. So what we're trying to do is not predict the future. We're trying to help decision makers and policy makers be better prepared for the future. So what actions do we need to take now to be prepared for the future? So other 2 things that are interesting is regional versus single node. So we could say, well, what is the best for each municipality versus what is the best for the actual region? So that's something that's further than the standard IRP used in South Africa. And then another big extension of a typical IRP is customer resource. And that's what we're going to be focusing on today, where we're saying that it's no longer a captive market. Solar PV plus storage has really changed. It is a disruptor in the industry. So it's not just what Eskom or the utility can provide, but also what the customers can provide. Thank you, Kim. Next slide. So just to give you an overview of the bigger project, again, so we've got the standard 4 different phases. If looking from status quo to forecast analysis, capacity expansion, and impact assessment. So those are sort of standard for most projects, nothing too new there. But you'll notice on the left, we've got the 4 entities, namely customer, technology, local resource, and utility. So we purposely put customer on top, and we've separated the customer from the utility via technology and local resources. Again, as I've mentioned, it's no longer a captive market. It's not just what the utility provides to the customer, it's what the customer can also provide. So you'll see there under 2 forecast analysis and the customer, you've got rooftop PV analysis, and that's what we're going to be doing in today's presentation. Next slide, please, Kim. So to find out what the PV potential is in the Garden Route District Municipality, it's got sort of a 3-step process. The first one is to say, what is the technical potential based on available rooftops? So this is sort of a physical analysis of saying, well, how much roof space is there? How much usable roof space is there? How many PV panels can we pack on that roof? And then specific yields based on the solar resource. So that's step one. Step two is then to say, what is the business case for this? Because essentially, we're not just interested in what the physical upper limit is. We're interested in what step three is there, is what is the adoption rate. So you'll see step two and step three have been noted as work in progress. So what this presentation is going to look at is we're going to look at, first of all, the input data for step two, and then we're going to conclude with what we actually did in step one to try to quantify the PV potential. Next slide, please, Kim. So the first step that we do with any kind of energy planning or energy systems modeling is to get to know your customer. So we got to know the customers through the municipalities. So this is, you see the Munich sales. It's not that important that you sort of look at the focus on the numbers, but we can see for the whole region, items A to G are the 7 different municipalities. And what we're looking at here is the total number of customers on the left. So for the region, around about 150,000 customers. But you'll see on the bottom left that in terms of number of customers, the residential obviously is the largest portion. But when we move to the right, we can see that although residential is the largest number of customers, because industrial and commercial customers are much more energy intensive, their share is much greater. So residential then drops to around about 50%. You'll see the total annual sales of 1.1 terawatt hours. So to give you some context, this is less than 1% of the national demand in South Africa. Next slide, please. So that's the one side is the municipality selling to the customer. The other side is Eskom selling to the municipalities. So on this, we obviously, because of the losses, which is less than 10%, which for municipalities is actually very good. We're looking at around about 1.3 terawatt hours and a peak demand for the entire region of 250 MVA. What's interesting to note on the bottom, you'll see a graph which is splitting up the off-peak in blue, standard in orange, and the gray is peak demand and peak in terms of your energy consumption. And it's quite interesting that every municipality believes they're different and unique, but their time of use always looks pretty much the same with the 40:18 ratio. Next slide, please. So solar PV costing, and this is something, so we're doing this work from the CSIR, as you'll see, and Subway is really well positioned to actually provide guidance on this. These are the current solar PV costing that we use, and you'll see later on when we talk about learning rates, we've actually given you this is the high, and then we've got the low version as well. So this is what we're seeing as more conservative. At 27 Rand a watt for residential, for commercial and industrial, 20 Rand a watt, and utilities 15 Rand a watt in today's value. So the next slide will show you the learning rates that have been applied. So that's next 20 years. So on solar PV, in terms of utility, there's not a shortage of data sets. So we see there's quite a few. But in what we use for the study is sort of an average of 3 different data sets. You'll see that's that middle yellow line there. That's what we use, which is quite a significant drop. And the next slide shows the residential learning rates, which will have slightly less data sets. But you'll see that again, we've used a sort of middle of the road approach, but we're seeing that the residential sector in terms of CapEx is expected to have a more steep decline in terms of costing. So then we take all of this learning rates, we take what the current costing is, and we can then forecast what the cost of the CapEx is going to be into the future. And you'll see on the next slide that I believe we use the low value. So these are, for instance, the first ones with the high values, and these are sort of what the low hazard values we're using of 20 Rand, 15 and 12 Rand. So just quickly, we're seeing quite a large reduction there of around about 46% by 2030, and then sort of 54 sort of plateauing or declining slightly less. But essentially, what this study is showing, or what the data sets are showing, is for utility we're looking at under 9 Rand a watt by 2040. Thanks, Kim. The next slide. So in terms of the solar resource assessment, obviously that's dependent on the local resources. So we can't just take some sort of generic value based on a national average. We actually can go and look at each different municipality individually. And again, what we came back to in terms of the extension of a standard IRP, which is the nodal, which looks at one point. It doesn't have a geographic factor to it. What we're seeing here is that anyone that lives in the area knows that sort of near the coast, it's a bit more UK kind of weather. There's a reason why it's so green. But if you move up the escarpment, for instance, going from George to Oatsworthing, there's quite a bit more solar resource. So the question that we wanted to answer in the study is it better to put the PV generation at Oatsworthing and move to George, or leave it at George, which is the highest demand center? And on the right, we're seeing some annual capacity factors. It's still work in progress. I think they'll probably drop a little bit there. Next slide, please, Skip. So that was the inputs into determining the business case model. We've also then looked at demand projections. We looked at tariff projections in terms of what we think Eskom's pricing is going to do. Those are additional slides, but we won't be discussing it. So in terms of, again, going back now to the rooftop PV potential, we first need to say, well, how much roof space is there? So you'll see on the next slide, it's quite a data intensive. So even that is approached in two different ways. The first one is saying the megawatt meters squared. So this is sort of, you can go measure the roof space and say, well, this is how many square meters are. But the ultimate question that we're trying to answer is, what is the potential for PV? So how many PV panels can you pack on that roof? And that's where we get to the point B, where we go from meters squared to megawatts and megawatt hours based on the specific solar resource in that area. So I believe the next slide then will be the GIS. There we go. Okay, so to determine available roof space per municipality. So this is quite a data intensive exercise, and it's geospatial, so it's all done by the GIS experts within the CSIR. So there's a few data sources that you use. First of all, the municipal boundaries. It's fairly straightforward. And then there's quite exciting, and I'm not sure if everyone knows about it, but there's the recent Google Open Buildings data. So what that Google Open Buildings data is, what you're seeing on the right there, is those yellow figures and the blue figures. That is Google that's gone and scanned the skies and scanned satellite data and used AI and machine learning to figure out which of those are actually roof spaces. So in this figure, you'll see here that the yellow is commercial and the blue is residential. All that A is trying to show is that there are sometimes with the data that it'll take a single roof and sort of divide it into smaller roofs. And B, you see there, it slightly missed some of that roof space there. But we did quite a lot of quality control and looking at the data of this, and we actually feel it's a good confidence in terms of giving an approximation of roof space in the area. And then obviously the last one, like you've seen there with the customer classes. So we're trying to distinguish between residential, commercial, industrial, which is what you're seeing between the blue and the other. So then we put that all in, do a lot of GIS work, and then you'll see on the next slide, it comes out with a lot of roof space. So it's in meters squared, and we're looking at millions, just to give you a context there. Obviously, the larger municipalities, for instance, George and Mossel Bay, have more roof space. That's nothing really surprising. We'll, in a few slides, we'll give a bit more context to what this actually means, because I mean, 9 million meters squared, I don't really have a feeling for what that means in terms of kilowatts or kilowatt hours. But what we're trying to just of residential, and that's true for all customers. So the blue, which is on the bottom, is the proportion of residential versus the commercial versus industrial in the gray. So the next slide, we'll see then. There we go. So it's one thing to take the yellow blocks or the yellow polygons. Obviously, we can't just take that and say, well, that's great. That's the amount of roof space there is. We need to say, well, how much is useful roof space? So you can see, for instance, some of the spacing, and what we actually did is we actually go in a very data and, well, let's rather say labor intensive exercise of actually going and counting the roofs, then sort of classifying them as, you know, is it north facing? Is that south facing? Every kind of south facing roof is then excluded. And then we get a proportion of all of these yellow areas. What do we actually can we classify as useful roof space? So again, it's lots of manual sampling. We did it for all municipalities, for each customer class, and we actually included agriculture additionally as well. And then we'll give you sort of the outputs of then saying, well, of these, what you could almost call the GIS outputs of that 9 million square meters, how much of that is actually useful? I think the next slide then tries to give an idea of how we got to that. So what we're seeing here is the blue blocks on the top. So again, what we said is we're just going to normalize this and say, so we got the GIS output, the 9 million square meters, So let's normalize that to 100 square meters so that we can sort of say, well, the whole point is to get to the right and say how many kilowatt hours, or let's first say how many kilowatts can we install, and then how many kilowatt hours are we actually going to get from that PV installation. So let's just say we start with 100 square meters. Then based on the sampling, and this is unique per customer class, per municipality, you get to what we classified as reasonable roof space, which is around about a 35% decline in the region. It slightly varies per municipality, but not particularly too much variation. Then we included an additional loss of 25%, just mainly because of shading and structural and abstraction issues. Obviously, you would need to go and look at each roof individually, but we use that as approximation. So of the 100 square meters, you're looking at what we then call the usable roof space of 50. So you're looking at a 50%. So half of it is usable. And then so we're saying, well, that's great. How many PV panels can you pack on it? So we took a certain size PV panel, which is a certain rating, 2x1 and a 325 watt panel, which is actually pretty much the panels I've got on my own roof. And then we say, okay, what does that translate in terms of installable capacity? So how many panels can you pack on your roof, which then gives you an 8 kilowatts in this example, which then based on the specific yield, that is an average of the region, which is around about 20% capacity factor, gives you 11,670 kilowatt hours, obviously on the AC side. So that's the process. So now the question is then, so how many PV panels can you pack on these roofs? And then the next slide answers that question. So here we see, it's not a particularly interesting slide, but there's actually a lot of information. We should make it look a bit more wow in the future. So determine the technical potential based on available rooftops. So what we're seeing here, this units now is megawatts, and megawatts AC. So for the entire region, if we had to go and say, we had to go over the whole garden route and we had to install on every single of those roofs that have been identified, PV panels, how many would we actually get to? And then the answer is around about 1,750. So quite a lot. If you recall the total demand, peak demand in the garden route district municipality is only 250 megawatts. That's 7 times more than the MD. Obviously, we're not with solar PV, it's not firm capacity. So that's not what we're really interested in. It's more of an energy saver or energy provider. So the question then would be, well, how much of that translates into kilowatt hours? So again, what we're seeing, obviously, because of the more roof space, it's residential, it's got the highest potential for installable capacity. So on the next slide, what we did is we just applied a thought process. Thanks, Kim. Sorry, you can't see that. So what it's actually saying there is how much of installable capacity is required to provide 100% of customer energy consumption. So again, now we're not talking about megawatts, we're talking about megawatt hours. So again, we have that same installable capacity of 1,750. And what we identified is said, okay, what is your annual energy requirement in magnitude? We're not saying solar PV is going to provide electricity at night. We're just saying how much electricity do you need over a year? X amount. So then to get to that X amount, how much percentage of your installable capacity per municipality, per customer class is required? And again, what we're just showing on this figure is that on the residential side, so overall, there's ample space. So the simple answer is around about 36%. So if you had 650 megawatt PV, you'll be able to provide the annual customer energy consumption in the region. But then to look at it more specifically in terms of customer class, in terms of residential, commercial, industrial, we see that there's ample roof space for residential. Is fairly low, so there's lots of roof space for not too much electricity demand. Where on the other side, we're seeing that there's not enough roof space for industrial. Where industrial is obviously the roof space to energy is a different ratio. So their roof space is a lot lower per kilowatt hours used. But again, what we're saying is we're not saying there's not enough PV to provide industrial. We're just saying there's not enough roof space. So obviously, if you move to ground-mounted systems, then it'd be a totally different situation. But our whole purpose was to sort of provide, again, as Frank mentioned at in the beginning, is to find decision and policymakers to play. The question we wanted to ask it is what role or how big a role can solar PV or rooftop PV play in the energy future of the garden route district? And our answer is it can play quite a big role. Obviously, the work did not include storage. On the utility scale, we will include storage, so that will be included. But we feel comfortable that at least the decision makers and the policy makers know that there is a fair amount of potential in the Garden Redistricting Municipality, in total 1,750 megawatts. So then the next question, or the next process of the study, which I won't be presenting because it's all work in progress, is then to find out, we're busy with the business case, and then ultimately say, well, of this installable capacity, how many of these customers are actually going to start adopting electricity? This is obviously a much more gray area, but it's something that we're exciting to work on, and we'll be working on in the next week or so, and I look forward to reporting on that. So thank you for your time.
Thank you, Warwick. Much appreciated. Maybe just to throw one question in there quickly as a thought exercise. I mean, what do you think? Do you think it would be feasible within the next decade for the Garden route to almost go off the grid, to actually build all the solar and perhaps throw in some storage and actually be grid or Eskom consumption neutral?
So we've got different scenarios, and again, this is now looking at the utility scale, so not the rooftop PV analysis. We're looking at the utility scale in terms of capacity expansion planning. So what do we do with the Plexos modeling? So the short answer to that is the first scenario we run is a business as usual, just Eskom. So that gives you sort of your baseline. The next one is a least cost option. You say, well, Plexos, tell me what we've given you these technologies, we're giving you the costs, we're telling you what the learning rates are. Tell us what you believe is the least cost option. And what we're finding is that the least cost option and the two other scenarios, which is decarbonization and autonomy, is sort of what you're saying there about how much do they need to do to become independent. The least cost option is pretty much covering the other two. So it's not becoming a question of if this is solar PV, it's a nice thing to do, or it's a little bit greener. Solar PV plus batteries, which is what we included in the utility scale, is providing a least cost option for the municipality, for the region.
Okay, great. That's super exciting, and I think
and that's before 2040. It's not like it's that far away.
And it's not that far away. So great, thank you, Warwick. Much appreciated. And we'll perhaps ask more questions in the Q&A session. We will jump over now to, I think, which will flow in quite nicely from that, is Johan from Solar F is going to talk to us about defection from the grid. And just quickly to give you a little bit of Johan's background, he holds a master's degree in electrical and electronic engineering that he got from the University of Johannesburg. He initially worked as a research engineer for a company called FP7. It's actually not a company, it's a research entity where he was doing R&D around aerospace technology. But in 2014, he got involved with the South African renewable sector, and in 2019 joined Solar F, which is a leading provider of CNI solar and battery solutions in South Africa. And he currently leads the commercial and technical development of energy storage projects, in particular at Solar F. So thanks, Johan. Over to you.
Thank you, Frank. Thanks for the introduction. So yeah, there was some talk in the office on the topic whether it's deflection or defection from the grid. But whatever your reason might be, it means the same thing. We were looking into ways of being free of the grid, in this case in Eskom, but I want to talk about it a bit more holistically. We can jump into the first content slide, please, Kim. So we're all fairly familiar with Eskom and their shortcomings, and I think that pretty much paints the picture for why. Why do we want to defect or deflect from the grid? It's obviously reliability and availability concerns, but if you take a step back, there could be other reasons as well. Even if the reliability is there could be some commercial or cost motivations. If you've got a cheaper source, then of course that's one of the reasons why you might want to consider. And of course, the green reason also, if you want to move away from a carbon-based generation, it comes down to the same thing. We're all looking to go as far as possible off-grid or completely off-grid if possible. So on the next slide, we dig into this a little bit, and I'm using a retail operation as a high-level case study here. A retail operation which peaks at about 1 MVA peak loading, and this is something that works very well in the PV market, purely because the generation and the consumption profiles line up quite nicely during the day. There might be some peaks in the morning and in the afternoon, depending on whether this retail operation includes restaurants or other sort of nightlife operation. But in general, the two line up quite nicely. Of course, this graph will vary slightly depending on whether it's commercial or residential as well. But looking at retail operation, we can see that as you start installing panels, every panel increases your benefit, and that goes pretty much linearly until your generation and your load matches up, at which point you'll start over-generating, and as is up to now mostly the case, you cannot sell that energy back to the utility. That means the system will have to start curtailing. One way to work around that, of course, is to include storage, but now you see that all of a sudden, your cost goes up. So again, typically 40 to 50% of your base load, really depending on what that might be, can be covered by grid type PV fairly easily. But after that, you need to start adding a way of spreading that energy that you generate to move your whole site closer and closer to being off grid. So what we call solar penetration. So it's fairly clear that the cost increases the closer and closer you get to being off-grid. And that makes it less commercially interesting. However, from a green point of view, that's what we want to do. We want to have as high amount of renewable energy in our energy mix. So we need to find a way to marry these two. And I guess that comes to our first, we've got the ideal, and that's our first roadblock that we need to overcome. Next slide, please, Kim. So if you look at the applications, typically when we engage with customers, there seems to be an understanding or a way of thinking that the moment you've got storage or batteries, that this is for backup only or for off-grid operation only. And that doesn't need to be the case, of course. I'm sure we'll be discussing this topic a lot, but just briefly, there are other ways of using your energy storage in the forms of energy arbitrage, where you're going to be charging your battery at night and during the day, preferably from a renewable source, and then releasing that energy again during the peak time periods in the morning and in the afternoon when the cost is the highest. And that obviously gives you a very good commercial case. The other option is peak shaving or demand reduction, which is where you cap the consumption from the grid at a certain point. So once your demand exceeds a certain value, that additional energy gets supplemented from renewables or from storage. And then lastly, which is I think the most holistic case, is if you've got any additional solar, you will stick that in your battery and you'll run that off once your PV disappears at night. And you can run your facility for as long as you've got energy left in the battery. So these are cases where you can combine these with a backup solution, and then you get the benefit from both worlds. So you get that green benefit, but you also get something that starts to make more sense from a business case perspective. Next slide, thanks. So yeah, the roadblock clearly is that deflecting from the grid is expensive, but the nice thing is that energy storage is very flexible. So we can and we do apply this in ways that marries the two, and marries the green ideals along with the other green, which is the money, the capital ideal, the commercial ideals. So to implement this, it starts off with technology selection. And then I think data as was presented is incredibly important. So we like to do a lot of microgrid modeling because you're moving into a realm of where you've got multiple energy sources, PV, grid, battery, potentially generator as well, where this starts to resemble a microgrid. And to find an optimum, you really need to look at those numbers quite carefully. Next slide, please, Kim. So from a technology perspective, I think everyone is familiar with low voltage, more residential type solutions, which is a 48 volt based system. These typically have a limit. You can go as high as 100 kVA in certain instances, but I think a practical limit is 50 to 60 kVA. And this is purely based on your copper and your reticulation, which becomes incredibly expensive due to the high currents. So for larger projects, you definitely want to move to a higher voltage DC bus on your storage side. And if you're looking at something like a retail operation, then we want to go all the way to the highest voltage possible at the moment, which is 800 volts DC. And that also gives you a lot of flexibility because you've got larger inverters available. You can build much larger systems, which of course gives you that higher solar penetration that you're looking for. So to understand how all this works, we do a lot of microgrid modeling. And just as a quick example, for this retail operation that I mentioned, you'd see that the customer load, being the red line, exceeds 500 kVA. And this was sort of a magical line, purely because that was what their supply was limited to. And in this case, we're supplementing the council with both PV as well as battery energy storage when required. So it's a fairly dynamic thing, and we've got our own control system that we developed, which gives us that flexibility, and that also ties in with the modeling. So we can simulate only those buttons and knobs that we can turn on based on what the equipment can do. And in that way, we are free to design a system that can behave in a way that we like. So as you can see, as this retail operation expanded, the load started to increase and increase. And the moment that you see the council load approaching the 500 kVA limit, energy storage will kick in, and that will reduce the load to make sure that they do not exceed the maximum amount that they're allowed to draw. So from the simulated domain to actual data. So this is pulled off the monitoring system. And I'm going to look at 3 case studies of what we did using battery energy storage in combination with backup power. So the first one being maximum PV penetration. So this was a customer who was more interested in the green approach as opposed to the commercial case. And here you can see at night, starting on the left, so 12 o'clock at night, the battery starts off at an arbitrary state of charge. The black line being the load, which we cannot affect, but we can affect which energy source this comes from. So you can see the energy draw from council decreases as the solar picks up in the morning at about 5 a.m. And during the day, we're supplying the facility almost entirely off of solar. And any excess solar, which is the green going beneath zero, that's energy that gets then charged into the battery energy storage system. And in the afternoon, and this is the case, 17 November, so it's a week or two ago, where we had some thunderstorms in the afternoon. You can see now all of a sudden there's no PV available, so we start pushing that energy out of the energy storage system. So typically there are 2 limits that we then apply. The first is the soft limit, where we stop discharging the battery and keep a small reserve. So at around about 7 o'clock, the discharge stopped, but at 8 o'clock, load shedding started. So we had a small reserve that we can then draw upon immediately and run off for a short while. And once we reach the second limit, that's when we start the diesel gensets. And that'll pick up the building load. We'll run the generator as efficiently as possible to charge up the battery, not all the way, but to a preset limit. So in this case, 80%. And after that, council returned, but the battery was also charged sufficiently, and we switched back to municipal, to council power. So this is a typical day, but, well, not a typical day because of load shedding, but on a typical day, you would actually see that energy running all the way until about 10, 11, 12 o'clock at night, running off of the stored energy that was generated by PV. In the second case, this customer was interested in energy arbitrage. So it's fairly simple. The battery charges from 10 o'clock at night until about 5 o'clock in the morning, usually as slowly as possible to make sure that you do not affect the max demand too dramatically. And then during summertime from 7 to 10, we discharge the battery. And in this case, you can see the solar picking up quite nicely. So we're only discharging from battery storage early in the morning. And as the PV picks up, that contribution from energy storage becomes less and less. And then as during the middle of the day, we charge again using solar. And then in the afternoon from 6 to 8, we discharge from battery energy storage again. And so the cycle repeats itself. And obviously the cost differential between your peak tariff and your off-peak tariff, and in this case, your solar LCOE gives you that saving that you realize for every kilowatt hour that you arbitrage. And the last case, next slide, please, Kim. Maybe just one back. Yes, thank you. The last case is peak shaving, and that's the retail operation. So even though it's to increase the capacity, it is in essence at heart a peak shaving solution, and this is the actual measured data that we get from the site. So we can see as the load picks up in the morning, the solar PV also picks up, and we keep that draw from council nice and low, so we do not exceed the 500 kVA mark, which is the goal in this instance. So it's definitely possible to combine different energy mixes, and energy storage is therefore key if you want to increase the solar penetration and to move closer and closer to your grid deflection or defection. Because it's flexible, we can apply it in multiple ways, and that also means from a commercial perspective. So we can tailor the system so that you've got a good mix and makes good commercial sense. The biggest roadblock still being the cost. Even though it's more attractive, it is still expensive. So things to I think, if say next steps, is to find lower levelized cost of energy storage solutions. Something which makes sense to bring that cost of storing the energy as low as possible. Another possibility is load management and scheduling, and something which is not really covered in the scope of this presentation, but obviously I know a lot of people are looking at that, is including EV storage as a way of storing surplus energy or adding backup power into the mix. That's it from my side.
Thank you,
Frank, and thanks for the opportunity.
Yeah, and sorry, I think we're so used to hearing about grid defection that I assumed your title was defection, and in fact it was deflection. And perhaps it would be helpful if you could maybe just give your views in a little bit more detail why you spoke about deflection instead of defection, and any thoughts on defection, if I can pop that to you now.
Yeah, I think that really comes into wordplay. Defection sounds a bit more aggressive, I think, than deflection. I guess in a way they come down to the same thing. I guess deflection is a little bit softer and maybe a process that will take a little bit longer, whereas defection is probably a more immediate effect. Even though we know there are customers that want to definitely defect as soon as possible.
Okay, I think, yeah, let's talk about that a little bit more in the Q&A session, because I think
sure.
there's a lot that can be said about whether or not customers should defect, and I guess the ethics of that, or could they not become a more advanced form of prosumer if the right regulatory environment was in place to use their storage to support the grid. But let's talk about that in the Q&A session. So thanks so much, Johan.
100%.
We're going to
Thank you,
jump
Frank.
over to Garth Klutter now, who is the CEO of SBS Engineering. And he's going to be talking about a number of projects that they've worked on with battery storage across South Africa and Southern Africa. To give you a short CV, he's a business executive and renewable energies engineer with experience in business management, business development, business strategy, and as I mentioned, is currently the CEO of SBS Engineering. He's passionate about developing and optimizing business operations to successfully implement and manage the full life cycle of solar photovoltaic and battery storage solutions across multiple sectors and jurisdictions. Yeah, it's a mouthful, Garth. He has been involved in every facet of the project life cycle, including sales, development, scoping, design, procurement, implementation, and operation of solar PV and battery storage projects. And he has an in-depth understanding of both the commercial and technical requirements to ensure the successful and effective deployment of renewable assets for a wide range of off-takers. He's a firm believer that Africa needs sustained economic growth to shine on a global level, which can only be achieved with the right infrastructure, most notably of which is reliable, sustainable, and affordable power, which I'm sure he's going to argue comes from solar PV and storage. So thanks, Garth, over to you.
Thank you, Frank. I think that's very wordy. Okay, so yeah, I'm just touching on it, battery storage applications specifically with solar PV. I think I'll touch on quite a few of the same things as what Johan touched on, and he gave a very nice overview of it. And hopefully I can add a little bit more to what he's already presented. So in the market, what we're seeing at the moment is we're seeing numerous different types of applications of battery storage and solar PV. In different types of constellations and different sort of applications. So traditionally, we get a lot of phone calls of people phoning us up and saying, listen, we want to go off grid. There are varying elements to that and different viabilities to be able to do so. Battery storage applications, which I largely see, or and SBS largely sees, is going off grid, which is solar PV plus battery storage, to take a facility totally off grid. More traditionally, or should I say historically, when battery storage was significantly more expensive, a lot of the sites which we've worked on are remote lodges, out in the Masai Mara or Serengeti or up in Africa, where it's a 4 or 5-star lodge, and the clients actually just literally need to, or most of the time are running off of diesel gensets, and they need to create quiet times. So they utilize their diesel gensets, to generate energy, pump it into batteries, and then utilize batteries on a relatively small scale to create a quiet time for guests, and then go back over to their diesel. Then going on, we have on-grid applications for battery storage, which, as I noted, Johan mentioned a lot of these cases. So it's backup power, during load shedding or grid outages, tariff arbitrage, peak shaving, renewable energy production management, so utilizing your battery storage to further your renewable energy case. Then you have your utility type considerations for battery storage, being grid support or grid stabilization, utility demand management, which can also be done on a smaller commercial or residential scale. And then you have, battery storage, which you can utilize in a constrained grid environment, thus creating additional capacity with other forms of renewable energy sources. Kim, next slide. Okay, so the key drivers which we are seeing in the market as a whole, and it's not just South Africa, it's Africa as well as most of the world, is we're seeing ongoing increasing utility costs, which is obviously a significant driver. And everyone's looking, especially post COVID, is how to limit their costs, how to limit their OPEX. It's increasing diesel costs. Levelized cost of solar PV has been decreasing ongoingly. We're going through volatility moments at the moment where prices have increased a little bit, but in general, if you look at the last 10 years of trends and the future 20 years as Warwick presented, we're seeing an ongoing decrease in solar PV costs. We've got decreasing costs in battery storage, And then we've got grid limitations, especially in South Africa and up in Africa. Grids are either weak or there's limited capacity, generation capacity, or we're having quite a bit of outages, load shedding, stability issues, and that sort of thing. And then further to that, there's the whole social aspect. People want to be seen going green. We want to all reduce our carbon emissions. We want to look towards the future for the next 20, 40, 50, 100-year horizon and what's going to be happening with our planet. We want to go into sustainable operations. And there's, especially in the last few years, the last 10 years, we've seen significant trends towards going green. And there's far more awareness around it specifically. Kim, on to the next slide. Okay, so next slide. So starting off with off-grid applications. At SBS, we're very fortunate. We've done quite a few off-grid type systems, and this is one example thereof. Is we've got an island out in the Seychelles where we've built a 3 megawatt peak solar PV plant plus 6 megawatt hours of battery storage. And really, with that battery storage and solar PV, we're really creating an off-grid environment where we reduce the reliance on diesel. Now, as you can imagine, any remote site, the cost of getting diesel to these facilities is incredibly high. You either got barge costs, you've got trucking costs, you've got all the logistics, to get diesel out to these remote locations. So any form of renewable generation makes an impact. If we look at the next slide, the one option of addressing that is, your typical solar PV diesel hybrid type constellation, where you've got your solar PV, you've got your existing diesel genset fleet, and you utilize your solar PV to, feed in parallel with your diesel. Your diesel remains your grid forming devices, and your solar comes in similarly in your normal grid type application. With the diesel, acts as a diesel saver or, a cost saver device. And then in that graph on the right-hand side, you can see the typical impact thereof. It's very much subject to your irradiation on site and, what your ongoing load is based on your gensets and your necessary spinning reserves, but you're able to reduce the amount of diesel which you would have otherwise used. So instead of the black dotted line, which you would have had, from your diesel previously, you're sitting with that purple line. On to the next slide, Kim. So on this specific case and the next two cases, this is really what we're doing. So we're taking solar PV plus batteries, and we're adding to the existing diesel generator fleet to, off. What it does require, in these sort of circumstances, is because you've got using so much of that solar PV in your off-peak time, or your night time, you need to significantly oversize your solar PV source, to run in parallel with your batteries. The very rough single line diagram or schematic which I have there on the left-hand side is one example. There's lots of different configurations, DC coupled PV onto your battery, doing essential and non-essential loads and splitting up. This is just one specific example. And what you can see on the right-hand side in terms of that graph is there are periods where you're going to be running diesel. But to try and push for 100% renewable fraction in any sort of system, as noted by Johan, is incredibly expensive. You'll end up designing your system for, those 3 or 4 days of ongoing rainfall where you just don't get enough PV out. So you'll end up having to do, increase your solar PV size by 10-fold just to get an additional 1 or 2% renewable fraction or renewable penetration. So that's really your limitation. In these sort of systems, you do tend to have quite a bit of excess energy of solar PV, which you'll end up curtailing and not utilizing, unfortunately. But that comes down to, a simulation and optimization around levelized cost of energy. And that's really the driver for most renewable energy systems and battery storage systems, is trying to come up with the most financially viable, mix of energy sources to keep your costs at a minimum. If we look on the next slide, this is another system where we've done this. Basically, what on this site in Kenya, what we did is similarly, we took the consumption profiles, we did significant simulations, around the consumption profiles the utilization of the diesel gen sets, looked at what loads are deferrable, and we shifted around to create a profile which we could, significantly impact with solar PV and battery. Based on the consumption profiles of the site, the lowest cost of energy point, which is a mixture of the existing diesel plus solar PV, which you see in the photos, plus the battery storage, came to approximately a 92% renewable fraction. Anything additional over and above that, we found started pushing up the energy cost rather than decreasing it. Obviously, as levelized cost of solar PV battery storage changes, we're able to add on to these systems down the line. But at the date of construction and commissioning, the sweet spot, as we refer to it, was sitting really around that 92% renewable fraction point. Come on to the next slide. Similarly, we've got another system in the Seychelles, and I think we can actually skip this system going on to the next slide. So you really try and optimize your systems and your applications of your battery storage and your solar PV, around what is right for the site itself, based on the consumption profile and how to optimize and minimize that levelized cost of energy. Kim, on to the next one, please. Okay, so that is, traditionally what a lot of people have been looking at with regards to the application of battery storage with solar PV. It's going off-grid or minimizing that impact. Now looking at the on-grid applications, so we've got, the first form of on-grid application for solar PV plus battery storage is tariff arbitrage. And what is the fundamentals of tariff arbitrage? It's looking at when your energy costs more versus when it's cheaper. Now, on the left-hand side, or on the right-hand side, I think many of you would have seen these sort of wheels before, is your wheels with regards to your time of use tariffs. You've got your green energy, which is your off-peak periods, where energy is relatively cheap. Middle of the night, Eskom would like people to utilize more in those periods and less in the red periods, being the peak periods, to level the production requirements and the management of dispatchable power sources, ad hoc. So as such, to try and manage that, one of the methodologies which have been utilized is time of use tariffs. And you can see, in your high peak, in your winter season, your peak tariffs, between 5 and 8, and then in the evenings again, is incredibly high. Similarly, even in summer, you've got a much higher tariff for those peak periods than the off-peak. And tariff arbitrage is literally utilizing that mechanism to level out your consumption on site and decrease the cost or decrease the amount of energy you utilize in those peak periods. So you charge with your green energy or your off-peak energy, and then dispatch it into your red or your peak periods. On to the next slide. You can see a typical mix of how that is being done. So, you have your utility, your Eskom, your City of Cape Town, your Tshwane, municipalities, whomever is providing energy, on a time of use basis. You've got your solar PV production, and you've got your battery storage. And the big thing there is trying to, again, find the right mix of energy sources and the right sizing of your energy sources to reduce your levelized cost of energy and reduce, typically in this example, how to reduce the periods of, in that table where you're sitting between 6 and 9 or 5 and 8, your peak period consumption, and similarly in your evenings. So in this case, basically with the mix of solar PV plus battery storage, we've got almost no consumption, coming from the utility grid between 6 a.m. and 7 p.m. in the evening, so with a mixture of the solar PV plus battery. So, starting on the left-hand side at midnight, we're slowly charging the battery storage. Again, similar to what Warren said, to Johan said, is charging the battery as slow as possible, not to create any peaks in the maximum demand. And then as we get into the morning, where your initial peak tariff starts kicking in, you start dispatching that storage and you push it, and you can see that in the green solid line section. We start pushing that energy into into the grid. At the similar time, we've got the solar PV, which starts generating. And then up until, in peak period, we're dispatching that storage and we're utilizing the solar PV to make sure that the consumption from the utility grid is as reduced as possible. Then going into your standard period or your midday, your daytime period, we'll end up utilizing to cover most of the site's consumption. But any excess solar PV, we start putting into the battery storage. So we start charging up the batteries again to dispatch into the evening peak. And that's what you can see us doing there later in the afternoon after 4 p.m. We start dispatching the battery storage, again pushing into your peak period or your late standard period and your peak period to reduce that impact. And then going into your off peak in the evening, going back into charging the batteries. Okay. So that is one typical example of utilizing battery storage plus solar PV specifically for tariff arbitrage, reducing your standard rates and reducing the amount of energy you consume during peak periods. Okay, relatively high consumption during off peak. Okay, on to the next slide. We see it at this specific site, actually here in the Western Cape. We've implemented, the system to do exactly that. We've got about 200 kilowatt peak of solar PV, which is oversized for the facility, and the consumption on site almost by about 50 kilowatts, or kilowatt peak, should I say. And then in parallel with that, we've brought in 200 kilowatt hours of battery storage. And we do, we charge the site, during the night with off-peak, during off-peak periods, we charge into the battery, we dispatch into the morning peak, we take the excess solar PV, and again, we dispatch that stored energy into the evening peak, thus reducing, the overall demand of the facility, and as well as the standard and peak periods. Okay. On to the next slide. The other example which we have is peak shaving, and the peak shaving is sometimes a difficult one. It is very much dependent on the site-specific profile. The example which I've shown here in the slide, which you can see in front of you, is I've pushed the peak into the morning period. So that a lot of bakeries, for example, you've got a significant amount of baking which starts 5 a.m. in the morning, for the morning rush. So all of a sudden you've got this massive spike in consumption on the facility, and then that spike decreases. But as some of you would need to some of you would note, sorry, I see Frank is noting that I'm running a little bit behind. So I will try and speed up and answer any questions afterwards. Is, what we really do in those sort of constellations is we try to find ways of decreasing the peak demand of the site, and we utilize the battery storage to pump specifically into when the maximum demand would be of the facility itself. You can do that with solar PV, you can do it with battery, but it really depends on what the consumption profile of the facility is. If the site has a very flat consumption profile, it becomes a lot more difficult to impact the maximum demand with diminishing returns. Kim, on to the next slide, please. Okay, the second last type of application which I want to make is renewable energy production management. So onto the next slide. I've touched on it already, but where you start oversizing your solar PV, or you want to push a higher renewable fraction, and typically most sites, in and around the country, without exporting significantly, and having normal solar PV grid type system, we can impact, say, a 30-35% renewable fraction. If you want to start creating a higher renewable fraction, then you need, without excess, I want to say, wasted energy into utility grid without any returns, we start oversizing the PV. What we need to do is we need to bring battery storage in. So what we do is we put battery storage onto the facility. Any excess solar PV, we feed into that battery to be then utilized in the evening, or non-sunlight hours. And that's what you're seeing there is the yellow is the excess PV, which is not utilized to service the main consumption. All of that PV goes into the battery and then gets utilized, after 3 p.m., after 4 p.m., when the consumption or when the solar PV starts decreasing. On to the next slide. Okay, so the final example, which I want to touch on is constrained grid environment. What we're seeing more and more, across South Africa and many of the countries in Africa is generation is limited. So either substations are at capacity, they cannot handle any more consumption, or alternatively, there isn't infrastructure, or the grid as a whole just doesn't have any additional generation capacity left over. Load shedding being a prime example, we've started hitting the caps of what is capable in the system without spare capacity, for volatility, etc. So the other example, which we're starting to see more and more of, is environments where industries really want to still obviously produce. They want to build factories, build facilities, create income, create jobs, but they're being told by the utilities, we don't have capacity. So what the other option is, we start bringing solar PV plus battery plus wind, whatever forms of renewable sources in, to be able to create additional capacity for the site. So on the graph on the right hand side, you're seeing the utility has said the site is limited at 500 kVA capacity from the utility. So anything over and above that, we need to generate through the solar PV plus battery storage. And generators. The last thing you want is to have 3 or 4 days of bad solar resource or low wind, and all of a sudden your facility needs to shut down. So in those moments, you'll run your diesel generators. But really, what you'll end up doing is you have excess PV. The excess PV then feeds into your batteries, and then you utilize all of that capacity which is fed into your batteries to create the additional localized production for the facility. Okay, so rounding off, as I noted, I'm running a little bit out of time, is, there are a lot of different ways of cutting that pie and, applying your solar PV, battery, wind, hydro sources, throughout sub-Saharan Africa and South Africa to really address the site-specific needs. But what it does require is quite a bit of engineering consideration around the different sources of energy. The different sources of energy add some level of complexities. There's control requirements, but what it can do is create quite a bit of flexibility around your applications, depending on what sort of grid connection you have, what are the costs of energy, how can you optimize your OpEx costs going into utilities, energy production, etc., and really finding the right balance to manage your overall costs. Thank you.
Great, thanks, Garth. Much appreciated. You can almost go back to being on holiday, on leave shortly. But please do hang around for the Q&A, because I think there are some questions we can propose to you then. So thanks very much. We're going to move over to Dr. Svet Bajelkov. I'm probably mispronouncing your surname, so please correct me, Svet. I see it's misspelled on your presentation as well, so apologies for that. But he's going to be speaking to us about the monitoring and analytics that can go around looking after batteries and how that can help rapidly scale up renewables. He is the CEO and co-founder of AMMP Technologies, where he leads a team that are dedicated to streamlining the management of distributed PV hybrid systems. And they provide software that enable owners and operators to truly integrate energy data into their workflows. Svet was previously the Chief Technology Officer at E.ON Offgrid Solutions, where he worked on quite a number of PV mini-grid deployments and other operational projects across sub-Saharan Africa. And as you can gather from the doctor component, he holds a PhD, interestingly enough, in atomic and laser physics from Oxford University. So I'm sure it could be a whole interesting conversation there as well. And he also has an a Master of Science in Theoretical Physics from Datam University. So Svet, it sounds like what you're doing is actually super interesting compared to what super simple compared to what you studied, but maybe it isn't. But yeah, I look forward to hearing what you've got to say. So over to you. Thank you.
Thanks a lot, Frank, for the introduction. Physics is interesting, but I think what we're working on here is much more important in many ways. And I look forward to telling you a little bit about it. My presentation actually, I think, segues really nicely from some of the ones that we've seen just now, especially from Johan and Garth, about these deployments into, you know, how do we actually scale this up? What are the kinds of systems and software that we need to put in place to do that? As Frank said, I run AMP. I started the company with my co-founders a couple of years ago after running off-grid systems, battery solar systems in a few different locations around Africa. We decided that it's time that we have some proper software for this. And in some sense, we think of it as the operating system for distributed energy. I'm going to start by giving you just a few words about what we do, and then look at a really nice case study that we did on battery analytics for PV battery systems in Africa. Kim, next slide, please. Yep, so thanks. Maybe the next one. Very briefly, in some senses, what we do is your typical monitoring example. We acquire data from different kinds of systems. So we do PV, of course, battery, diesel, grid, any kinds of sensors that you might want to have. We do analytics and aggregation on it, and we feed it into you know, the full suite of operational processes that many of the companies dealing with these kinds of assets will have. So both the technical operations and commercial operations. Next slide. Thanks. So at the heart of it, on the acquisition side, we have integrations with pretty much all of the major vendors that obviously help us get the data. Next slide again. Thanks, Kim. And then what I'd say really kind of sets us apart is the actual modeling that we're then able to do with that data. And kind of already from the start, we had the storage and the PV components baked in. So we know we didn't start with PV monitoring and then kind of add on the other things. From the start, we appreciated that the systems that we want to work with are complex. They will have a number of different sources of energy generation and usually some complexity around the offtake of that. So that's all baked into the way that we deal with that data. Next slide, please, Kim. And just in a nutshell, a couple of other things that I think are a little bit different about the way we approach things. The way we get data from these systems is both via API integrations with the vendors, which mean that we don't actually need to install any hardware at most sites. It means that we can kind of do a cloud-to-cloud integration between, you know, the SMA or the SolarEdge or the Fronius monitoring or the Tesla monitoring and our platform. But of course, we do also have data loggers that can be deployed if that's necessary, if it's a more complex site, for example, or if there are specific requirements on data granularity, or if you're trying to bring equipment that's offline, such as a diesel generator or some sensors online. And then, as I said, we translate these into a number of different kind of insights that operators of these systems can use. So whether it's real-time performance monitoring and uptime monitoring, or longer-term reporting, billing, things like that, or even custom interfaces. You know, if somebody is running on a mall and wants to have a screen in the mall that shows how much renewable power they're generating, you know, those are the kinds of interfaces that we can build on top of the data hub that we've collected. Next slide, please, Kim. And in a nutshell, what we want to do, you know, the mission is to allow these businesses to scale profitably, streamlining the work, bring everything into one place, really cutting down those operational costs. And in many cases, we did the study, we found that we can reduce O&M costs for these sites by up to about 30% by simply having better processes around data management for those. Thanks, Kim. Next slide. And yeah, just in a nutshell, where we are actually based in the Netherlands. We monitor systems, about 1,000 systems, kind of really globally, but Sub-Saharan Africa is our main market. And at this point, South Africa is where we're really kind of doubling down on growth and looking to also open an office there in the next few months. Thanks, Kim. Next slide. So first, I just want to say a few words on the case for storage. Next slide. You know, this is pretty commonly kind of understood, but of course, battery costs are falling. You know, we wouldn't be having this conversation today if we aren't seeing the trends that we are. They're forecast to continue falling by something like another, you know, almost 50% over the next decade, as we saw in some of the previous presentations. And we've seen that ourselves. I mean, with AMP, we are now monitoring around 450 systems across Africa that incorporate batteries. So we've seen that kind of uptake ourselves in a kind of hands-on way. Next slide. And then the use cases, and I'm not going to go into that because both Johan and Garth did a wonderful job of explaining why you might want to have batteries. I'll just highlight that what we see most often, what we look at most often also in the analysis that we did here, is systems that do a combination of backup power. So if there's a grid outage or temporary grid outage, the batteries can kick in and cover for that. And then also what I guess we've called here maximum self-sufficiency. But again, this concept that when you install a PV system and you're not allowed to feed back into the grid, you want to be able to operate that system at maximum output and be able to store that store that energy in your batteries and then dispatch it, for example, during the night and maximize your solar output that way. I think next slide. And just one case study here. I'm not going to dwell on that because we saw quite a few really cool systems. This is one system in Kenya that we've been working with by a company called Offgrid at a tea farm. So yeah, 1.5 megawatt solar, 4 megawatts hours storage. And they really installed that for purely a commercial purpose to reduce the electricity costs for this large tea producer. It was mostly a displacement of diesel in that case. So they have Tesla power packs, SMA PV inverters, a DAC generator control, and of course, a grid connection. They were to use this to get cleaner, cheaper, more reliable power than they were able to previously. So again, just yet another case study of how deployment of storage in the right situations can be very beneficial. Next slide, please, Ken. Right, so this is then just getting into sort of the meat of the presentation here is doing advanced battery analytics. The next few slides I'm going to present are a sort of a synthesis of a white paper that we published based on a collaboration with a couple of different companies I'm going to talk about. But the purpose at a high level was to really see how we can work with battery data and get insights from it that really allows this scale up, this profitable scale up of battery technology across many sites and across many different use cases, because we are believers in the idea that if this was really to have an impact, we need to move away from having these individual sort of niche applications and figure out how we actually scale this across a number of different sites. Next slide, please. Oh, yeah. So what we did here was look at 14 CNI systems. This was in Nigeria. These were operated by, or are operated by a company called Pirano Energy, which is a developer, financier, and operator of PV and PV storage systems in Nigeria. These were a little bit on the small side, so between 3 and 15 kilowatts of PV and 5 and 30 kilowatt hours of lithium-ion batteries. And we looked at 11 months of data from these systems. And we did this in partnership with a company called Acure Battery Intelligence, who specialize in battery analytics. So Pirano were the people who installed the systems and were running them. AMP was the team that essentially gathered that data and was doing monitoring of those sites. And then Acure was the company that looked at that data and did the analytics. As a little bit of background, Acure is a sort of spin-off from one of the premier battery technology sort of data centers in the world, which is in Aachen University in Germany. And we also have a couple of folks on our team who previously worked there as well. So maybe yeah, just to one last point I wanted to make about the case study was one of the interesting things for us was to see, can we do this in a way that's scalable? So first of all, we wanted to do it without any additional hardware, using just the data that's kind of natively available from the monitoring systems of those inverters. And can we do it with the sort of data set that we can get practically? So, you know, it's data that wasn't very high frequency data. We were only getting data points about once every 5 minutes without any additional battery management or monitoring system. So literally just the simple voltage, current, state of charge, temperature. And also having even data outages where, sometimes for a few hours on end, we weren't getting any data. So there was a question of, here's a test case. Can we get something useful that comes out of this? And this is what we set out to do. Before I go into the results, just a quick primer on battery aging, which was one of the main things we analyzed here. So the aging process of lithium-ion batteries mostly comprises calendar and cyclic aging. Calendar aging is literally what happens when the battery is just spending time in a particular environment, so a particular temperature, a particular state of charge. And that process happens regardless of whether you're charging it or discharging it. And then cyclic aging is what happens because of the charging and discharging cycles of those batteries. And in most of the PV battery applications we've seen so far in Africa, it's calendar aging that tends to be the most relevant. We can go into that in the Q&A if that's of interest. And maybe just to stick with the last slide for another minute. In terms of the calendar aging, the high temperature and high states of charge are the main drivers of aging there. They are what accelerates the aging process. It's a little bit counterintuitive almost, especially for anybody coming from the lead acid battery world, where you know that a low state of charge is what causes degradation. Here in lithium ion, you don't want to have a 100% state of charge battery just sitting around. So that's what would cause aging. And then of course, on the counterpoint, if you cool your battery and if you have a charging strategy that are based on kind of consumption forecasts, that can improve your operations. Great, next slide. So the main takeaways of what we did, firstly, this isn't on the slide, but we were successful in getting some really valuable insights from this data set that we monitored, that we measured over 11 months. Despite the limited sort of data points that we had, the limited resolution of the data, we're able to translate that with Akira's help, of course, into some pretty granular and what we felt was pretty reliable state of health estimations and aging estimations. We did find then that aging varies significantly based on operating conditions, and you kind of know that, but actually doing the analysis and seeing it and actually getting the data out was really insightful for us. And one of the most eye-popping things then was that out of the 14 systems, we found that one was basically on the brink of failure just 2 years after installation. And I'm going to say a few more words about that. Next slide, please. So in depth, and maybe just starting with this chart on the right, what we did was over these 11 months, plot the state of health of these different battery systems. And of course, so the state of health, by the way, is a rough measure of the capacity of the battery compared to its initial capacity. And when you get to a state of health of about 80%, that's essentially considered end of life. And of course, for the majority of the battery systems, we could see some gradual degradation happening over time, pretty much in line with expectations. But there was this one example where we saw that a system lost about 12% of its original state of health over the period in which we're monitoring it, which is, if you're an operator, which is really not a great thing to find out, although in some sense it's a good thing to find out now rather than when the battery event basically fails. We of course then looked at what is causing this, and we found that this system was operated at fairly high temperatures, usually around 35 degrees Celsius. And also a fairly high average state of charge. So it spent, if I remember correctly, something like 90% of its life at a state of charge that was above 95%, which is, again, something that we know theoretically accelerates aging. So of course, if the operation doesn't improve, this battery would be reaching end of life within the next year or so. And of course, if you've installed this battery just 2 years ago with the expectation that you're going to get 7 to maybe even 10 years of life out of it, that's a surprise, and that doesn't reflect well on your commercials either for that project. So Pirano, based on these insights, were able to improve the cooling strategy and also tweak the system a little bit so that it was spending less time in this state of charge to try and nonetheless prolong its lifetime. Next slide, please. And yeah, just sharing also some feedback from their O&M engineering team. They really appreciated the granular overview that they were able to get here. And of course, these insights that were ultimately able to extend the lifetime of their batteries. So this is a monitoring project that we're now continuing to pursue with them going forward. Thanks. Next slide. So I've just kind of given a recap of this white paper and the case study that we did. The full white paper is available on our website. So if you go to aamp.io/news, you can get that there. And then there's quite a few other publications that may be helpful. So we, for example, have a battery monitoring cheat sheet that literally just goes over what are the most important things to look at when you're looking at battery data. Next slide. That was it. Thank you very much for following along, and I look forward to doing some Q&A shortly.
Great, Svet. Much appreciated. And I have one or two questions for you, so we'll ask that in the Q&A. We are running a little bit behind time, so I'm going to jump straight over to Glynis Kutsia from Genesis Eco Energy Developments, who is going to talk on a project spotlight around storage. Is arbitrage, in fact, a viable business case? And just a little bit about Glynis. She has a bachelor's degree in architecture that she got from the University of Cape Town. She's a member of the Chartered Institute of Buildings and holds a Certified Manager of Community Associations qualification from CAI in the USA, and has been in the building, design, construction, and sustainable development sector for nearly 30 years. Glynis has worked for a large corporate software development company, implementing engineering software products both in South Africa and in the USA. And she has run her own property development business, providing professional design and construction industry-related services. She has project managed a number of residential and boutique commercial property developments and refurbishments with an emphasis on sustainable design. She has extensive experience managing residential security estates, implementing renewable energy and water recovery and conservancy solutions into these environments. She currently works as a project development executive for Touchpoint Energy, which is the division of the Genesis Infrastructure and Renewable Energy group of companies. And they provide utility, smart city, and small-scale embedded generation energy solutions, including solar, energy storage, wind, and micro hydro projects. She's also a freelance writer and has had several articles published in a variety of local and international art, engineering, industry, construction, and lifestyle magazines. So, Glynis, that's wonderful that such a rounded area of set of interests. And so very much look forward to what you have to present to us today. Thank you. Over to you.
Thanks, Frank. I think that introduction was longer than my presentation is going to be. But let's get started. So thank you very much to you and the audience. We just want to cover a case study for the arbitrage, and we've approached it more from the business case point of view. So I'm not on the technical side as much as I'm on the having to make the projects financially viable and work. So from that point of view, we had a brief from a client that we needed to obviously assist them with load shedding mitigation and savings with a PV solar solution where possible. So I'm just going to go through this case study. It's a little bit on the financial and calculation side, but it is also an interesting journey for us to see whether this would work the way we imagined it might in terms of PV and storage. So the project, it's a production plant in South Africa. The important points, obviously it will be different for each case, but in this case it operates 24/7, Monday to Sunday. And importantly, a very flat load profile, consistent consumption. So bear that in mind when we get to the outcomes. So the consumption of the plant was about 1382 kilowatt hours, and the NMD charge was about 7,400 Rand a day, is about 7,000. And so with the load shedding mitigation, we had to work with those parameters. Next slide, please, Kim. So for the financial model, we have some assumptions. We worked on a 20-year power purchase agreement model. We're using P50 yields. The plant cost was about 60 million, and our for this particular project, our objective was 13%, and we're including the renewable energy certificates in the financial model to see if that assisted in the viability in any way. Next slide, please, Kim. So we looked at this project and we said, okay, the PV solar system size, we designed it to 2.84 megawatt peak, and we had quite a limited area on the site of the company. We used all the rooftops, we used carport structures where possible, other parking areas, and ground mount to an open area adjacent to the main plant. And we discovered that even with all of that, we could not oversize the PV plant to charge batteries. So we then decided to address it in a slightly different way. Next slide, Kim, please. Thank you. So Garth covered a bit of this in his presentation, time of use tariff structure. We had a look at that and determined their blended tariff and when we could use the off-peak periods to our advantage. So next slide, please. So here's a bit of calculation. I'm sorry if the image is a bit small. So we literally took every hour of every day for a year period, and we put in the Eskom tariffs or the municipal tariffs for the time of use that they would be paying. And this is obviously the low demand season. Next slide, please, Kim. We then did it obviously for the high demand season and had a picture of what they would be paying per kilowatt hour over the entire year per hour. Next slide, please, Kim. We then did a calculation as to the consumption figure. You'll see that little consumption figure in the middle top, 1381.67 kilowatt hours. And we show the values for each hour of consumption, time of use rate, what we would be paying or being able to essentially sell it for. So that's how we applied this model. It's relatively crude and simplistic, but we wanted to test this case. And we said we will calculate the kilowatt hour values at each hour of the year. Next slide, please, Kim. So we came out we sized the battery to a 1.2 megawatt size battery to meet the consumption requirement. And we essentially came out at a scenario where we will be buying 7 hours off peak, allowing for round trip losses. So at the minimum amount of cost, and then selling back to the plant at peak for the 5 hours of peak. If you remember the wheel, it's those 5 red hours and 1 hour standard. So essentially the PV solar system and the battery were essentially independent of one another in respect of the model. We did obviously determine that their NMD peak would increase by about 50% when the battery was charging from the grid. So we had a look at having to include that as a cost. And we then looked at a weekend premium charge to apply because the battery needs to be cycled throughout, and we'd have a negative value. Next slide, please, Kim. I think this explains it a little better. So we were buying 7 hours off peak. That was the real cost for that over a period of a day. Selling at 5 hours peak plus 1 standard. The NMD daily charge, which is about 50%, we had to add back. And so we netted out per week or per day. That shows a week's value, the net figure that we'd be able to realize using the arbitrage model. You'll see those 2 weekend premium, the weekend premium figures, they're negative figures. So we apply that to charge back to the customer in terms of the battery arbitrage. Next slide, please, Kim. So we then applied it to the whole financial model. And so we've got two parts of the project, which is the PV solar saving costs. So with that P50 yield and the municipal tariff being at about R1.24, the cost that they would be paying to the municipality about 5.5 million over the period of a year. We were able to bring our PV solar tariff to about R1.10, and therefore they would have a saving in the first year. This is year one. Obviously, cumulatively, it would get better. But the saving, we were able to determine about 635,000. We subtracted back that weekend premium that we would recover having to cycle the battery. And the net savings in the first year would be 323,000. It doesn't seem like a lot, but over the, as I said, it's cumulative. And with the other assumptions of escalation of 13% for the municipality tariffs, and which we also applied then to the arbitrage figures, the total savings over the PPA period for the company would be 228 million approximately. And but importantly, their load shedding mitigation brief would be met. So yes, it's not ideal in respect of not all the battery is not being charged with PV at all. There may be some excesses, but we based it purely on the PV solar component, making up the savings that would allow for the arbitrage, the extra cost in the arbitrage process. I hope I've made that clear. Next slide, please, Kip. So that's just a little graph showing the savings, the cost to us, so the orange at the bottom. The green part is what they would normally be paying the municipality or Eskom, and the net is the savings. So, and as I said, we added back the renewable energy certificate. We were able to get an NPV based on cash flow for the project of about 70 million with a 60 million rand spend. So that's good because it's a positive figure. Next slide, please, Kim. And this is essentially the secret to some degree. We're using the NAS battery technology for this. The reason why we chose this is because of its 100% depth of discharge ability and minimal degradation at the cycles. So I hope I've covered it clearly for you, and we were pleased to be able to offer our customer a viable project that we're comfortable in terms of the financial model, comfortable with in terms of the financial model. Thank you very much. That's me.
Well, that's great, Glynis. Thank you so much for presenting on that real world project, which is great. It's exciting to see all of what's being done with storage, both in South Africa and elsewhere, and at different scales. So thank you to all of the speakers so far. And that really brings us now to the Q&A session. So if I can ask everyone to, all of the speakers to go on camera so we can see you again. I'll perhaps start with the questions that have come through on the Q&A and the chat. Perhaps Mike Barker, who's I think well known in the industry, asked, or at least made the comment that a stable grid is a sign of an advanced civilization. Grid defection is societally inefficient, and we must reject elitist isolation. So I guess the real question is grid defection, leaving the grid to do your own thing, is that ethical? What do you guys think about that? Anyone like to answer that question?
I would, if I may.
Please, thank you, Glynis.
The straightforward answer is no, especially not in a developing country such as ourselves that we have, because we need essentially a large proportion of population to be subsidized in this regard, and if there's too much grid defection, then that won't be possible. So that must be considered.
So maybe a corollary question is do you think that the current Eskom and municipal tariffs encourage people to stay on the grid, or do they encourage people to leave the grid the way they're currently set up? Johan, maybe you can answer that one.
Yeah, my feeling is it's sort of in the middle. I think South Africa's energy cost is definitely not is much cheaper compared to other countries, but I wouldn't say it's high enough to really make the business case very easy to say, well, it's cheaper to go off grid. Let's do it. So I would say we're reaching a tipping point, but we're not there yet.
Okay, so maybe more to be done by municipalities and Eskom around their tariffs there. But do you think it's actually viable that a owner of a PV battery plant could actually add value to the grid and provide services to the distribution company? Dennis, maybe that's, sorry,
no,
you were going to say something.
I'm not going to answer that one. I'm going to just comment on the other one. I think the grid defection is, from the bit of research that we've done, is effectively around reliability of supply at the moment rather than cost, very much so. Done not empirical study, but certainly the feedback we get is that it's not so much about the cost. People would be prepared to probably bear a little bit more cost if they could have a reliable supply, and because it's essentially the loss of the lost opportunity costs of the businesses having to not operate and work. That is the problem, not so much the actual tariff.
Agreed. Warwick, you want to add to that?
Yeah, Frank. So I have a background a bit more in cost of supply studies. So this is a key question that comes up with municipalities very often is, we're worried about our revenue stream. We're seeing solar PV being installed. What do we do about it? And my personal opinion on this matter is that don't resist it. So I really believe the municipalities need to be dynamic in this and forward looking and not try the stick approach of trying to deter people from putting solar PV or batteries on, but they must rather go with the carrot approach of saying, how do we incentivize our customers who are now a customer resource? So this, I can buy from Eskom or I can buy from my customer. Why don't you incentivize that customer to want to do that? Mike's comment, I'm not sure if you should use the word ethical or not ethical. I think it's everyone should do what's in their own.
Sorry, the ethical was my add to his question.
Sorry, okay. But I believe that everyone should do what's in their own best interest. I'm a bit of a capitalist, but I believe that the team stay in terms of the grid is in everyone's interest. But that needs to come from what the tariff signals are being sent by the utilities to the customers.
Johan, you want to add some color to that?
Yeah, I think it really depends on, there are different angles to this. If you're taking the green approach, then renewable energy is much greener. So does that fall under defecting from the grid? It really depends on how you look at it. But on the other hand, yeah, a cost is very, very important as well.
Absolutely. So I think in summary, I do think it's quite possible for grid operators to construct their tariffs in a way that actually protect their revenues, but also promote prosumers or multiple sources of generation and storage on the grid. And hopefully we will see more tariffs emerging to support that in the near future. And then Jason from North Face Solar asked, what are your thoughts on using geysers as thermal batteries to store spare power once chemical or electric batteries are full? Has anyone worked on projects using hot water as an energy battery? That's my add to the question.
I've no formal experience, but it's definitely a novel approach. I mean, if you do have excess PV and you've got nowhere else to store it, heating up water is definitely useful. Whether you can extract that energy, again, I don't just think heating up your geyser would suffice. I think for thermal energy storage, you need much higher temperatures. whether that will be viable in a residential or small commercial environment, I'm inclined to say
so
no.
I would support that. I think he's more just saying that you know, you can capture the extra energy in hot water for use as hot water, and perhaps the hotter the water, the less hot water you mix with cold water when you are showering. Garth, you want
Absolutely.
to add to that?
Yeah, so we worked on a couple of facilities where, you know, we use hot water, or, you know, at least the heating of water specifically for as a deferrable load effect. So there are certain cases where it makes sense that, you know, the site is going to utilize that needs hot water. You know, either they can do heat the hot water cylinders at a later stage in the day, but during periods of excess PV, rather take that excess PV which you've already paid for and you've already you've had that upfront capital cost for, and pump that into that excess energy into heating water and utilizing it whenever you need it. And it is a very viable source of deferrable energy effects.
Right, thank you, Garth. And then a question from Richard Chizonga asking, and I think this is in off-grid projects where you're running a diesel generator and PV, is there any risk of reverse voltage or reverse power to the generator? And then my add, I mean, can this lead to generator failures? Has anyone experienced or had issues with generators and reverse power from a PV battery plant?
I would say if done correctly, no, there shouldn't be an issue. But it has happened before.
Well, let me ask
that
this
it has
question.
been done
What if
incorrectly.
you have, what if your battery and your solar is running at a certain, let's say 1 megawatt to the load, and the load trips and you're running the diesel at the same time? You'll have an instantaneous 1 megawatt surge from your load trip that's going to be absorbed perhaps by the diesel. I mean, is that a risk, or are the EMS and control systems, the energy management systems, good enough and fast enough to manage something like that? Maybe Garth, you can answer that one, since you've done many of these big off-grid projects.
I think it comes down to designing and modeling the system correctly. You know, so having excess capacity that can absorb, either, if there's a trip, number one, or number two, large cloud cover we've seen how it can cause massive spikes in excess energy, which needs to go somewhere. So it's designing the system such that, number one, your system, the reaction speeds of the control systems, reaction speeds of the batteries, PV, etc., are all in line to be able to manage that and handle that, number one. But number two, that you also have the capacity, some form of capacity, to be able to absorb that excess energy. And often the reaction speed is that needs to go into the battery storage system. And that's how we largely design most of our facilities, is there is an element of excess capacity available for that specifically.
Okay, great. And then perhaps, obviously I think most, storage is new and we're seeing a lot of new batteries deployed, but we're also starting to see second life batteries come out of vehicles and other applications. So Nathan Bergman is asking if, in particular, if SolarF or SBS, but I think maybe Svet could even comment on this, if there's a value proposition from an LCOE perspective to use second life batteries. Any thoughts on that?
I think there might be. I have to be honest with you, we haven't seen it happening yet on any of the projects that we're working on. I think people are probably a little bit iffy about how exactly to approach it. I know there are plenty of companies that are looking at the whole sort of value chain and recycling or repurposing old batteries into new ones. And I think it's mostly for kind of larger scale stationary storage, where the performance of any given unit isn't quite as important. It's mostly, you've got a lot of space and you can install a bunch of batteries. And if they, you can kind of balance out the operation across all of them. We haven't yet seen it take off in the markets that we're active in. I'm not sure if any of the other panelists have.
Johan, Garth?
We have not. I think there is a space in the market, but I can't say that we have too much experience, especially in the CNI space. It seems to have good value in the residential space, but so far we haven't seen a fit in CNI.
I would echo that. I think there is, similar to what Svet was mentioning, I think there might be application for it more on the utility scale, where there is, capacity and you're looking for grid support, etc. And we haven't really seen an application at least at this stage in CNI specifically.
Okay, great. And then I think this question for Svet from Manfred Kuster, saying that lithium battery manufacturers, and this is probably true for all battery manufacturers, but lithium battery manufacturers are not known for providing reliable information on guaranteed battery life. And does your battery analysis confirm this view? And perhaps I can color that by asking, I mean, do you see round trip efficiencies of batteries matching the specifications as well?
Yeah, it's a good question. I'd say that by and large, I would take battery specifications with a grain of salt, especially when you're operating them under, let's say, practical conditions, which are often not the ideal conditions that have been prescribed during whatever tests were done to get to the initial lifetime. In some respects, I mean, because we've been looking at even the performance of different battery chemistries over a few years now, it's almost too early to tell. The number of large lithium deployments that are out there, or that have been out there for a long time, are still quite limited. And there's so much evolution in technology that the battery that you're going to buy today is quite different to the one from a few years ago, and you just don't really know. What I would say is I think it's important to make sure that you are looking at how your batteries are performing ideally, and making sure that it has a good trajectory to optimum lifetime, and you're not operating at the wrong temperatures, etc. Some of the really easy ones there. But yeah, I think the jury is still out on where, how exactly we can make sure that we get as close as possible to the efficiencies. But no, don't trust what's in the data sheet for sure.
Okay. Johan, Garth, in your projects where you've built batteries, I mean, would you back that up? Are you seeing batteries perform to the specifications on paper in the real world? Yeah. Maybe Johan first and then Garth.
We are always cautious with what we read on the data sheet. We have started testing batteries at some point in time, and we've seen varying results. So that is one of the points where we like to align with more specific suppliers. I need to also choose my words carefully, but yeah, it's good to check. I think it's good to be diligent and question what you see, because yeah, it doesn't always do what it says on the tin.
I would echo that. I think everyone needs to be critical. Especially going with reputable suppliers, making sure checking track records, confirming what you're buying or what you're getting is what you're buying, and vice versa is always very much critical. We've had experience in off-grid specifically projects for numerous years. We've had projects where the batteries have failed significantly faster than what we would have liked, and we've stood by that and replaced batteries accordingly, which is never a fun position to be in. So we've dealt with those sort of situations. So it's going down to doing your due diligence, making sure you're getting what you're paying for, and that it's meeting the specifications of what you're supposed to be receiving. Visiting, checking other with regard to the specific applications, making sure both the control systems as well as the battery technology itself is well application, and then thirdly, testing. Going through the process. There's quite a few of our type of business between Solar F, SBS, Solar even, which goes through extensive processes with regards to testing facilities, testing batteries, and making sure that what is landed in South Africa or in Africa makes sense for the applications.
Cool. I'm going to just ask two more questions, and before we wrap up, and I'll hand over to Defection. So apologies to others who may have asked questions. I'll try and answer those questions that you may have posed in the actual Q&A session. But I think an interesting question from Dermot Murphy, who's perhaps from a competitor company at Sun Exchange, but asking, what is the best way to test installations of battery energy storage systems? What tests should be done at project acceptance, and then also at the end of year 1 and 2? Any thoughts on that? Maybe from anyone who's interested to contribute. Or should I pick on Svet? Svet, maybe you're a bit more independent in terms of the testing.
Well, I think Garth was about to say something, so I think you should go first, and then maybe I can add something to that.
Sorry, so I think this is an ongoing discussion in the market in general, and I'm going to jump in there. I think there's quite a few considerations with regards to, I think solar PV testing has become relatively clear, between the European experience versus, flowing over into the States, but as well as into Africa. So I think that aspect of it is clear. In terms of battery storage specifications, I think, number one, I think the key test which really needs to be done ongoingly is confirmation of capacity. Number one, is the capacity there which you expect, based on specific state of rates of discharge, rates of charging, and run a full cycle test, with regards to the storage which you have. A lot of the applications which you've seen, it's very difficult to do a proper, capacity test. But then, the other option is isolating portions of the facility and doing those tests, in sections, that you can at least get comfort ongoing that, number one, the capacity is there. Number two, the degradation is in line with what expectations were.
Great, thanks, Garth. And then just perhaps the last question before I hand over to Nivesh for closing remarks, from an anonymous attendee, but he says he needs advice. He's really interested in learning more about solar PV and renewable energy. What would you recommend as a path to having a fuller understanding? Any recommendations how someone can get into this industry and learn more? Where should they start?
Is anyone going to say PV green card?
I was about to say PV green card. It would be the first step to getting a feel and understanding.
And Dara, I might even pick on Devesh to answer that question. I see him coming online. So maybe we could do that, Devesh, if you can have present some just quick thoughts on that, perhaps as part of your closing. And just as we hand over to Devesh, just from my side, this has been a great session. Thank you to all of our panelists. Really appreciate the time and effort to be here. I think it's been a great time, and appreciate your time. And so it was great from my side. So thank you very much. Over to Devesh. Although I suspect Nivesh might be having some bandwidth problems now. Right at the end, Nivesh, you there?
Sorry, Frank. Yes, I am. Thank you so much. Yes, I think these sessions were designed to start sharing information with new entrants into the market. So we wanted to really pack these sessions with lots of information that people can learn from. The PV Green Card program has also set some skills development aspects for people to learn through to entering into the market. But I'm going to leave that there. I'm sure people are welcome to reach out to any of us on the panel to find out more information or get more insights. But again, just from my side, Frank, we've got 2 minutes before we have to close the session. So thank you to you and the speakers for a very insightful session. From the discussions today, it is clear that solar PV and energy storage is creating an attractive solution for our future energy needs. Market trends show that this combination continues to grow in popularity, and today's presentations articulated the various possibilities in the South African distributed generation market segment. The future is bright, and as we look at more opportunities to advance distributed solar PV and energy storage agendas. So just as closing remarks, as many may know, SAPIA is the representative voice of the solar PV industry. SAPIA is constantly working towards collaborating with stakeholders across the solar PV sector to share knowledge and drive effective change. We have today officially come to the end of this series of webinars entitled Driving Distributed Generation. Our commitment to drive the residential, commercial, and industrial market segments to take up more distributed solar PV generation in South Africa aims to build local competence of global standard and accelerate the local renewable energy markets. For those who have followed the series, the program has been well thought out and planned to cover relevant and important topics. In the spirit of knowledge is power, our aim is to share as much information as possible to encourage the participation in driving this distributed generation agenda. So as you can see from the slide in front of you, we have covered 6 themes over the last 6 months, each with an average of 5 focused topics. We saw 33 industry leaders from all spheres of government and industry providing useful information. The series was well attended with more than 2,100 registered participants. And Frank, a very big thank you, firstly to the SAPIA team led by Ms. Kim Thomas for the smooth running of these webinars, to our members who have participated, you, Mr. Frank Spencer, who we've heard from today, Ms. Chanda Kumalo and Mr. Maloba Cheshla, who have contributed and participated across the series. Our support consultants, Zoni Experiential, led by Ms. Nokwanda Nzamande. You will see a slide on her company. She's a young Black woman-owned entrepreneur in the marketing space. So please, let's support her as well. Our partners, the Mineral Council and the Intensive Energy Users Group, the sponsors who have made it possible for us to allow free participation in these sessions, Genesis Eco and Rand Merchant Bank as free sponsors, as well as Trina Solar as a session sponsor to 2 of our webinars. Much gratitude to every speaker who took the time and effort to share useful and relevant information, making our tagline, knowledge is power, a reality. And most especially, thank you to the participants for attending these sessions and making them useful over the series of webinars. So lots of people have been asking what's next, what can they look forward to from SAPIA? We will be taking a break from the webinars for the next few months while we focus on launching the Solar Power Africa conference and exhibition that you see on your screen. We've partnered with Messe Frankfurt, South Africa, who will be hosting this show. Please look out for your invitation. We will be sharing invitations in the coming weeks, and join us in Cape Town at the CTICC, the 18th of February 2022. We have an exciting agenda planned. There's 20 sessions with over 120 industry leaders and government officials that will be speaking on various key discussions. So with that, Frank, thank you. Thank you to you and the speakers. Thank you to the participants for tuning in. Have a great rest of the day.
Thanks, Deficiency. Cheers, everybody.
Thanks, everyone.
Thank you, everyone.
Bye-bye, everyone.